welcome to the second Smart Street webinar. My name's Kevin Hoban and I'm the project team leader on Smart Street. Just to quickly run you through the agenda for today's meeting, I'll be running you through a quick introduction and overview of Smart Street, and then I'll hand you over to Damien Coyle, who'll give you a technical update on the project, and in turn Damien will hand you over to Dan Harbour, who'll run through the trial design. Following that, there'll be an opportunity for some questions and answers. The webinar format will consist of 30 to 40 minutes presentation by the team, and then this will be followed by an opportunity for 10 minutes of questions. There are two ways that you can submit questions, either in writing at any time during the presentation, or if you've dialed in, you can press 01 on your telephone at any time during the meeting to allow you to participate in the live questions and answers at the end of the webinar. Just briefly looking at the innovation strategy of Electricity North West. Like all of the DNOs now, Electricity North West are moving away from a fit and forget network, which is very passive, to a more active network, which maximises the use of existing assets and utilising proven technology that is deployable today. This hopefully will generate better value for customers, giving them greater choice. Our Smart Street Grid development aims to deliver from our existing assets and give greater customer choice. We're fortunate that we've been able to secure over £36 million worth of funding from the ELC&F fund for our 4 flagship second tier projects. These are Capacity to Customers, Class, Smart Street and Respond. C2C was our first project, and this has now come to a close, and Respond is our latest project, which has just started in 2015. C2C, Class and Smart Street all look at demand response tied in with active network management. I'm sure you're all familiar with Smart Street by now, but just to give you a quick overview, as you can see on the slide on the screen at the moment, what the aim of Smart Street is we're looking at trying to flatten the voltage profile across our LV circuits using controllable devices and switches. On this diagram we can actually see 2 LV radial circuits which have been interconnected by a linked device in the link box. This is indicated by an L on the diagram. In conjunction with this, we're going to replace existing fuses with devices called WESAPs, which are basically circuit breakers. Again, so to give us greater control over the voltage on these circuits, we'll be deploying capacitors on the circuits and on-load tap changers at some of the distribution substations. This allows us to lower the voltage along the circuit. This in turn enables networks and appliances to work in harmony. The perceived benefits of carrying out this work is lower cost and quicker installation over existing technologies and reinforcement methods. Again, this has minimal disruption in comparison to traditional methods of laying more cable in the ground and upsizing transformers. This leads to a lower carbon footprint and hopefully will be invisible to customers, i.e. they'll gain the benefits without actually noticing a difference to their supply. Also a benefit of this is faster connection of low carbon technologies. Looking at the Smart Street project key activities to date, the project started in January 2014. This began with project mobilisation of the team, and the team was appointed, followed by contracts with the suppliers and project partners. Site selection was carried out and on-site surveys completed. The design methodology was developed, and then this methodology was applied to the trial circuits. This resulted in the final design of the circuits. Whilst this was being done, the customer workstream have developed a customer engagement plan which was approved by Ofgem. Also, the Smart Street website went live. Once the circuits were finalised, this made it easy to identify which customers would be participating in the Smart Street trials. And again, the customer workstream engaged with these customers on the trial circuits in the form of mailings. The technology installation has begun and the rollout of the kit on site has started along with some of the IT. Damien Coyle will go into this in a bit more detail later in the presentation. Looking particularly at the customer workstream on the project, this is split into 2 key areas. pre-trial and during or post-trial. Pre-trial, customers will have noticed an increase in activity on site as the kit has been installed. Also, a number of customers may see supply interruptions, although we haven't had to carry out any supply interruptions to date. Once we start installing some of the HV kit, this is a possibility. The main aim is to engage with customers to keep them informed and up to date with what is happening with SmartStreet so that they understand the need for the work. Some customers may see a reduction in lost time due to outages. This is in part due to the installation of the WEEZAPs replacing traditional fuses. In a scenario where we have a transient fault, the traditional method would have been to dispatch an engineer to site to replace the fuse. Now these circuit breakers will have auto reclose on them, hence in a transient situation we'll better get them back on supply quicker. There's a possibility that some customers' voltage will change, but the objective is to prove that the customers will notice no change in their supply due to this drop in voltage. So what next on the SmartStreet project? What progress have we made to date and what are the next steps? Customer engagement plan was submitted to Ofgem and was approved. The website went live, as we've already said, and the engaged customer panels were held and the lessons learned were published. These lessons were also used to produce leaflets which were then distributed to customers on the trial circuits. Customers who were potentially be affected or nearby the installation of the equipment received the secondary information informing them about the particular pieces of kit that were in their vicinity. A dedicated contact line was set up for customers to call in about specific SmartStreet installations so that the right information could be given to them first time in order to resolve these customer queries. So what are the next steps for the customer workstream? Next, the customer workstream will be briefing our contact centre before the trials go live. This will enable the customer contact centre to deal with any ongoing queries from the customers regarding the SmartStreet project. Further ECPs to engage with customers and perception and ability to deal with these will be produced, and a report will be produced to research these findings. Ongoing engagement will be carried out with the customers throughout the trial. I'll now hand you over to Damien Coyle, who will give you a run through of the SmartStreet technology and an update of where the project is today.
Thank you, Kevin. My name's Damien Coyle and I'm the SmartStreet technology engineer. And today I'm going to give a run through of what technologies we've installed, what technologies we still have to install, and then finally some of the lessons learned so far through the construction phase. The control system that will manage the SmartStreet trial circuits is called Spectrum, and this is provided by our project partner Siemens. Essentially, Spectrum is the brains behind SmartStreet. It'll take in all the field devices data and decide, depending on what trials we run at the time, how best to optimize circuits. The Spectrum system builds on learning from the class project on how we control voltage. The device you can see here is a WEEZAP. This device we'll be fitting these on the LV circuits at the distribution substation. These will replace the traditional fuse unit, and it offers three enhancements. One is control of the circuit. Two is the visibility of our LV network through the monitoring capabilities. And three is the advanced fault detection, which allows us to monitor faults on the circuit and react to them a lot more quickly, and also be proactive in tackling them. They can sometimes detect faults that haven't gone permanent on our circuit before customers go off supply. So this improves our service to our customers and our restoration. The Lynx device is an LV switch that works in tandem with the WEEZAP. This is the method on how we're going to interconnect our LV circuits, the meshing and unmeshing. They're remote controllable and will be controlled by Spectrum. And they also have monitoring capabilities, so they'll send all the details of the endpoints of those circuits back and give it and provide all the necessary information. They have the ability to control them locally and also remotely. What you're looking at here is one of the LV capacitors we've installed out on the LV circuits. There's 84 of these capacitors, 79 of them are installed on the circuits and 5 are installed at the distribution substation. The idea is that we'd have one installed on each ring, and also we'll be installing them on all the radials, and these are the devices that help us flatten the profile of the voltage profile. They are tried and tested. They were tested on our IFI project, and we've taken the learning from that and applied it to Smart Street. We'll be installing 7 HV capacitors. 3 of these will be ground mounted capacitors. These will be installed in the dense urban and urban areas, so the Manchester trial area and the Wigan trial area. They're quite large, and to improve the safety of them, we'll be housing them in GRP housings. There's 4 pole mounted HV capacitors. These will be installed in our rural areas, so that's Egremont and Wigton. And they're installed very similar to our pole mounted transformers that you can see out all our overhead networks. So just a quick overview of what's been done and what we still have to do before project go live. We've installed the 84 LV capacitors. We've refurbished 40 link boxes to enable the links devices to be installed. We've installed 50 endpoint controllers that feed back details of the voltage at the endpoints of radials. And our Spectrum 5 system is now installed on our network, and we're just testing this, so doing interoperability testing and test device function testing as well. So what have we got to do next? We have 7 HV capacitors to be installed. These are due to be installed in July and August. We have 5 voltage regulated distribution transformers, or OLTCs. These are due to be installed June, July and August. And then finally, we'll have the final integration of all the kit and commissioning up to the Spectrum system. So what have we learned so far from the construction phase? One of the learning points for us was the HV ground mounted capacitors. These being installed in urban areas and dense urban areas mean that there's a reduced amount of space available to install them. They're quite large units, and we didn't anticipate the exact size of them. And with housing them in a GRP as well, that increases the footprint along with the ancillary equipment that comes along with it. So we had to do a significant amount of work with landowners and local authorities to ensure we had the right wayleaves in place and planning permission. Similarly, the LV capacitors came in a standard size. What we found that in some areas where it's best to fit them electrically, sometimes it isn't best to fit them physically or in terms of what's on site at the location. And some of the locations we've had to reduce the size of the LV capacitor and bring the actual cabinet which it's in, or the housing it's in, reduce that. So that's one of the learnings that we've taken from Smart Street or built on the IFI. In terms of the IT, how we're running the project, we've got the Spectrum system, which is controlling all the Smart Street trial circuits areas, and this is working alongside our current NMS system, and they both work together and speak to all the field devices. So the interoperability between these 2 systems, and also how the data and controls are split between these, has been challenging for us. And one of the things we've learned is to have all manufacturers and project partners involved at an early stage to try and identify the issues earlier. I'll now hand you over to Dan Harbour, the Trials and Research Engineer.
Okay, thanks Damien. So my name's Dan Harbour, and I'm the Smart Street Trials and Research Engineer. And for today's agenda, I'm going to give you an overview of the trials and research work streams. So I'll start with a quick summary of the network design. I'll then run through the proposed test regimes to try and prove the smart street hypotheses, then the proposed 2-year test schedule, and for the research overview I will describe how we're planning to use the trial data and the production of these 3 main research work packages. So the smart street trial areas will consist of 6 primary substations. We have 2 located in Manchester, 2 in Wigan and Leigh, and then 2 up in the North Lakes in Wigton and Egremont. From these primary substations we will be utilising 11 HV circuits, and 10 of these circuits will have the capability to produce 5 automated HV rings. We will then be installing 7 HV capacitors. The 4 pole mounts will be primarily going up in the north region where we have a lot of overhead lines, and 3 ground mounted will be installed in the more urban areas of Manchester and Wigan. Further down those networks we will be looking to monitor 38 distribution substations. So these 38 distribution substations we will be installing a number of the WEZAPs that Damien has just previously discussed. At 5 of these substations we will be installing 5 OLTC transformers and 5 distribution substation based capacitors. These 10 substations will build up the 10 CVR test circuits where we can essentially raise and lower the volts at the bus bars. Finally we will be installing 79 midpoint capacitors out on the LV networks. The trial design is based around a 1 week on, 1 week off test scenario, and will run for a full 2 years. Essentially the 1 week off test scenario will provide a year's worth of baseline data, and for this baseline data we will be running the networks in the historic configurations, so i.e. radial configurations in historic tap positions with no automation. For the week on scenario, this will provide us 1 year's worth of smart street data, so this is where we'll be applying a number of our test regimes. The trials will also incorporate a number of customer surveys where we will be looking to assess the effect on customers' supplies, and we will purposely be carrying out surveys in a number of areas where they're not actually within the trial areas. This is to try and avoid a placebo effect that may occur knowing that you are in a trial area. The 5 trial regimes themselves will be used to test the full effects of the spectrum optimization, and these will include the LV and HV voltage control techniques. So essentially we'll be looking at how the optimization manages the OLTCs and the various capacitors out on the network. We'll also be looking at the LV and HV meshing techniques. So when we'll be looking at when the optimization decides to mesh or unmesh. And finally the final technique there is basically looking at the full optimization, so how we optimize the network from HV down to LV, and this will be involved in the previous 4 trials. So just to discuss in a little bit more detail on the test regimes, what we'll be looking to do for the voltage control techniques, we'll be looking to test each individual piece of equipment in isolation and then in combination with the capacitors out on the network. So as you can see, for the LV voltage control, we'll be looking to test the OLTCs in isolation in test 1, and test 2 we'll be looking to test those same OLTCs but in combination with capacitors out on the network. The same process will be carried out for the substation-based capacitors, and for the final test in the voltage control we'll be looking to assess the individual capacitors out on the network. For the network management and interconnection test regimes, we will essentially be comparing radial configurations with the optimized interconnected circuits. And for that final trial, we're looking at the optimization as a whole, we'll be looking to apply 2 different optimization techniques to the network. We'll essentially be applying losses reduction to the HV networks and to the networks where we can't carry out CVR, and then for those 10 substations where we can carry out CVR, we will be applying an energy consumption reduction. I should say for this final one, the universities will be carrying out a study on the interaction between the HV and LV and applying these two different types of optimization techniques. So how are we proposing to run a test schedule? This is still work in progress. We've got up till September to finalise, but what we're initially proposing is to run with an 8-week test cycle. So what we would do for the first 2 weeks, we will run with an off period, and this off period we will be making sure that everything, all the equipment is inhibited within Spectrum. We will run a test script to make sure that all of our networks are running as radials and our tap transformers are set at their historic positions. For week 3, we will then be testing the equipment in isolation. So we will be uninhibiting the specified equipment and switching in the optimization. And for week 4, we will be removing all inhibits and allowing the optimization to run across the whole of the trial networks. As you can see in week 7 and 8, we have swapped the HV and the HV voltage control techniques around. And this essentially will give us the full test scenarios of LV and HV voltage control. For trial 5, we will essentially be applying the optimization for the whole year where we are running the on period, but depending on the test scenarios from trial 1 and 4, we will only be able to optimize certain parts of the network. So week 4 will give us the full optimization scenario. So what are we actually planning to do with this trial data? The research work stream is essentially made up of 3 work packages, and these work packages will look at not only the electrical benefits, but it will look at the cost and carbon benefits. Work package 1 and 2 will be carried out by University of Manchester and Queen's University Belfast, where work package 1 will be looking to quantify the voltage and optimization techniques and the loss reduction techniques, and also looking at the interaction between the LV and HV circuits. They're proposing to do this by modelling all of the trial circuits in OpenDSS and then using the trial data to validate those models. Once those models are validated, they can then apply their various test criteria. Work package 2 will be using the same validated models, but for this they will then be looking at the meshed configurations. From the main deliverables from this work package will be to produce a design and an operational policy that can not only be used to roll out SmartStreet across E&W, but to roll across all the other DNOs across the UK. For work package 3, this will be carried out by Tyndall Manchester, and they specialise in climate change research. And they'll be carrying out 4 main reports. They'll be carrying out a techno-economic report, which will essentially be looking at the benefits of the optimization and any deferral to reinforcement. They'll also be carrying out a business case report, so looking at rolling out the technique across the UK. Also look at a cost-benefit analysis. So we're looking here at benefits to all stakeholders, including the end user, i.e. our customers, and then a carbon impact assessment. We'll also be using TNEI throughout the trial period. TNEI are our energy consultancy partners, and they have helped us throughout the bid and design phases, and we will have them now for the next 2 years to help out the universities with our research. So what are the next steps? From now until the end of September, we are looking to finalise all of the hardware installation. So all of the equipment out on site. We'll also be finalising the IT and the comms and the installation of Spectrum. And then the end of September we will start with the 2-year trials, where we'll be applying our various test regimes, and this will run in conjunction with the university's research deliverables. The end of September 2017, we will then have around 3 months to gather all of our findings, including the customer surveys. And then December 2017, we will be producing our closed-down report and disseminating our findings. So I'll bring back Damien and Kevin for our question and answer session now.
We have a question from Nikki Davis. Please go ahead. Your line is now open.
The issues that were incurred with regards to the street-mounted furniture and planning applications. I was just wanted to find out a little bit more on that, a little bit more detail on that, if possible. What sort of issues did arise with regards to planning applications, not necessarily the whaleys?
The applications was primarily regarding the HV capacitors. All the LV equipment we haven't had any issues with, so it was purely limited to the ground-mounted HV capacitors. So what we've had to do is secure leases for the 3 sites for those capacitors, which took a little bit of work, but we identified council land and they've worked with us quite well, and that seems to have gone okay now.
Just to pick up on what Kevin said, originally we thought we could have placed the units within our substation grounds, but where we were looking to place them on the network, the substation grounds just didn't have enough room in them. Taking into consideration, we're working in the Manchester area and in Wigan, so they're really densely populated areas where space is a minimum. So, but the substations there didn't, in some of our substations we've got lots of ground to work within, but in these areas they're very limited in their size, and that's why we had to pursue getting additional land. The LV capacitors, we're using 3 different sizes, 100, 150 and 200. We're switching them, they're controlled by a controller on site, which we take remote control of through the Spectrum system, and this decides when to switch them in. Now they do have the functionality now since we've started the project. The spec of them have been upgraded so they can switch in 50 kbar banks. Unfortunately, we'd already specified our control system and couldn't integrate this, so they'll be just switching in gangs, so it'll be all in or all out. So, but from the start we've done the studies, the network studies, to determine the best size of capacitor for that area. So all in all out was how we originally planned.
Yeah, it was mainly done internally. We did have help from TNEI. It helped us with the modelling, but it was mainly done through myself and our network strategy department. They'll be within Spectrum. Yeah.
Those are solely held within the Spectrum software, Siemens Spectrum software.
Yes, MR provide the voltage regulated transformers, OLTCs, and there's 5 of these units, so they're all 500 kVA we're installing.
The overhead line capacitors are rated at 500, and then for the ground mounts it depended on the network. So for the Manchester sites they're 200, and the Wigan is a 400.
We've had some customer feedback, one or two about the position of the street furniture, which we've dealt with on a one-to-one basis, and we've managed to resolve all those issues. Like I said earlier in the presentation, we haven't had to cancel any of the installations, and we've only had to tweak the position of a couple of the installations by 1 or 2 meters. So I think because we kept all that communication within the team, that allowed us to talk directly with the customers, give them the right information and resolve those problems. The driver is, and probably the driver for all the DNOs is that status quo isn't an option. With the developments and with the developments that we can see in the future, we need to be proactive in trying to come up with solutions to get more out of our networks. You know, in the past we've had very passive networks. We've just upsized everything. With the advent of solar power and the advent of heat source pumps and electric cars in the future, we do need to adapt and change.
The OLTCs are a tried and tested piece of kit which we developed on one of our IFI projects, or Tier 1, and they looked at operation. Obviously we've only had them out for 2 to 3 years now, and and these are new manufactured OLTCs we'll be using from MR. And every controller monitors tap operations, and we will be monitoring the usage of the transformers. We'll be monitoring the capacitors. All the devices will be watching how many times they're switched daily, and monitoring the health of those devices.
Just to add as well, I think we'll carry out a similar thing of what they've done in class. We'll take regular oil samples to see if there's any degradation.
I think, yeah, I mean, obviously we've secured funding for Respond, which started this year, and we're thinking about next year's projects as well. So I think Electricity North West is a forward-thinking company, and we're really going to be looking at as many things as we can to develop the network and change things for the future. I believe that's all the questions. So I mean, I personally would like to thank everyone for dialing in and listening to us. Thank you very much for dialing in.